Good morning, and welcome to day 7 of our AP Calculus free response question Advent Calendar. Be sure to check out the previous 6 episodes if you haven't already. There's a link to the playlist in the description. Let's go ahead and find the 7th chocolate on this calendar, and then we can get into today's calculus. There it is. Man, I tell you what, this has been a lot of work. So this chocolate will serve me well. Let's go ahead and zoom in on this chocolate number 7 here near the bottom of the calendar. And while I get into this square, I will put today's free response question on screen so you can give it a read before we begin. Today's question is some more integration, and it's one of those fun problems where we have to consider the volume of a solid with like a cool base and cool cross sections and all that sort of stuff. We got a white chocolate ball this time. You know, I'm beginning to think there aren't any bears in this box. There's bears on the box, but I don't see any bears in the box. This is just a ball. It's not a bear. There's a picture of a bear. I was expecting a bear. I wanted a bear. Whatever, man. Let me just have this dang chocolate. I still feel like my throat is kind of like sore from being sick like a month ago. And man, I tell you, this is just, life's hard. Life is hard. We got midterms coming up. Whole lot of work. But this delicious Lindt chocolate does lift my spirits. All right, let's get into it. This is free response question 2 from the 2004 AP Calc AB exam. This is part of the graphing calculator section, so we will be using a calculator throughout this problem. Let's read it. Let f and g be the functions given by f of x equals 2x times 1 minus x, and g of x equals 3 times x minus 1 times root x, for x between 0 and 1. And we're given a graph of these curves for free. You can see they go from 0 to 1. We have f of x as the upper function, that's right there, and g of x as the lower function. Part A is to find the area of the shaded region enclosed by the graphs of f and g, which is what we have a picture of. You're not going to get a much easier part A than this. We can already see a picture of this situation. We're trying to find the area of this region, and we can use a calculator. So all we have to do is take the integral of the upper function, f of x, so I'll write the integral of f of x, minus the lower function, which is g of x. This is going to give us the area between the curves, and we want this area from 0 to 1 because this shaded region goes from 0 to 1. Now, f of x, of course, is 2x times 1 minus x, and g of x is 3 times x minus 1 times root x. So let me just write those things in place of f and g. All right, so that there is the integral that we're calculating, and we will just use our graphing calculator to do that. So I'm going to press the math button, and that's going to give me access to all these functions. I'm going to go with function 9, the integration function, and we are integrating from 0 to 1. What we're integrating is 2x times 1 minus x minus 3 times x minus 1 multiplied by the square root of x. And we see from the calculator, this area is about 1.133. So let's write that. This is about 1.133. And that completes part A. Moving on to part B, find the volume of the solid generated when the shaded region enclosed by the graphs of f and g, so this shaded region here, is revolved about the horizontal line y equals 2. Now we know from the picture the horizontal line y equals 2 is somewhere up here, right? Because y equals 1 is right there. So we're revolving the shaded region about that horizontal line way up there. I've just done a rough redrawing of the figure that gives us a little bit more room to work with. This is our shaded region that we found the area of in part A, and for part B, we're creating a solid of revolution by revolving this shaded region about this horizontal line y equals 2. So that's going to look something like this. You can see how the lower curve, which is g of x, The lower curve is going to trace out the exterior of this solid of revolution. The interior is going to kind of be cut out by the upper function, which was f of x. As we do this revolution, it would look something like that. We have these middle circles cut out by that upper function. So this is what we call a washer problem. To find the volume of this solid, we're going to have to add up the areas of all of these washers. I said add up, and of course that means we are integrating still from 0 to 1, because we are still talking about this shaded region from 0 to 1, and what happens when we revolve it about a horizontal line. What we need to add up are the areas of all of these washers. And the way we find those areas is by taking the area of the bigger circle, traced out by the lower function, and subtract the area of the smaller circle, which is traced out by this upper function. Each circle has an area of pi r squared. Let's just take the pi out. So we have a pi in front of the integral, and then we're going to need the radius squared of the bigger circles, and subtract the radius squared of the inner circles. Now, what is the radius of these big circles? Well, that would just be the distance from the line y equals 2, which is the center, down to the curve that's tracing out the circle. That curve is g of x, the lower curve. So this radius here is just 2, the horizontal line, minus g of x, because it's the distance between the line and the curve g of x. So we'll put that radius in here. This is 2 minus g of x. That's the radius of the big circle. The radius of the small circle is similar. It's the distance from the horizontal line y equals 2 to the curve that's tracing out the smaller inner circles. That curve, of course, is f of x. So in here we'll put the radius of the smaller circles, which is being subtracted, and that's 2 minus f of x. Again, remember from the picture we see that g of x is that lower curve, f of x is that upper curve, which is actually tracing out the smaller circles. And here's what that integral looks like once we plug in the pieces. We still have the pi out front. We're integrating from 0 to 1, 2 minus g of x, and this is g of x. This is getting squared, minus 2 minus f of x, and this is f of x, and this is getting squared. Let's jump over to the calculator and find the value of this integral. Again, I'll press the math button and then go to function 9, which is the integration function, and then I will go through the long process of typing this whole thing out. You want to make sure you're careful when you're typing these long expressions with parentheses and squaring into your calculator. This looks right to me, so I'm going to go ahead and press enter, and we see this is about 5 3/20, but we don't want to forget that we took a pi out of the integral, so we also have to go ahead and multiply this by pi. Once we do that, we get about 16.18. I'll round to 3 decimal places and call it 16.179. That completes our solution to part B, so let's go ahead and move on to part C. Let h be the function given by h of x equals kx times 1 minus x for x between 0 and 1. Notice that h of x is just like our function f of x, except instead of being scaled by 2, it's being scaled by k, where k is positive. So it's either being shrunken down a little bit and maybe looks like that, or it's being stretched and looks something like that. Finishing the question, for each k greater than 0, the region, which is not shown, because remember this is f of x, it's not h of x, the region enclosed by the graphs of h and g is the base of a solid with square cross-sections that are perpendicular to the x-axis. There's a value of k for which the volume of this solid is equal to 15. So we could stretch this function h of x by some k that's going to make the volume of the described solid equal to 15. We need to write, but not solve, an equation involving an integral expression that could be used to find the value of k. This problem is actually pretty easy, but there is a lot going on here. We need to read it very carefully. Let's come back to our picture and draw what h of x could look like. Like we said before, it looks just like f of x, but scaled up by some factor, or potentially scaled down, but let's draw it as if it has been scaled up. So this is y equals h of x. Now the question is asking us about a solid whose base is enclosed by the graphs of h and g. That is the base. So this region between h and g, F has nothing to do with this at this point, remember? This region between h and g is the base of the solid in question. I'm going to erase this shading just so our picture isn't too cluttered, but just remember that f of x isn't important right now. It's this region between h of x and g of x that is important. The problem is saying that we have a solid, and the base of this solid is this region. And the way that this solid is constructed is by basically taking squares that lie in this region and that are perpendicular to the x-axis. That means it looks kind of like this if we were to take a cross section. That's perpendicular to the x-axis. It lies in this region, and the cross sections, as it says, have to be squares. They're square cross sections. So just to give you some of this 3D perspective, they might look something like this if we were to do kind of a rough perspective sketch of the cross sections. That's coming up out of the screen. It is a square cross section, and its base, the base of this square, we can clearly see is just the distance between the upper function, h of x, and the lower function, g of x. So this base, the side length of this square, is just h of x minus g of x. Now, what about the height of the square? Well, it's a square, so of course this other length is just another side length of the square. It also has a length of h of x minus g of x, because that's the base length, and this is a square, so it's equilateral. Thus, the area of the square is h of x minus g of x squared. To find the volume of this solid, which we know is 15 for some value of k, remember k is part of the definition of h of x, to find the volume, we just have to add up all of the areas of the square cross sections. So let's set up this integral. We have to integrate from 0 to 1 the areas of the square cross sections. The areas of the square cross sections are the squares of the side lengths. Each side length is h of x minus g of x. We have to square those to get the area. We're adding this up. This integral gives us the volume, which is equal to 15 for some value of k. Now, where does the k come in here? Well, let's just rewrite this integral one more time, replacing h of x and g of x with what those functions actually are. H of x is kx times x minus 1, and g of x, the lower function here, is 3 times x minus 1 times root x. And remember, this whole thing is the side length of the square cross sections, and so we need to square it to get those areas. This integral is equal to 15 for some value of k, and we could use this equation to solve for k. That's the answer to part C. And that completes our solution to free response question 2 from the 2004 AP Calc AB exam. I hope you're having a great December and enjoying the AP Calculus free response question advent calendar this year. Please do share it around with any other people studying calculus you know that might find it useful. I'll see you tomorrow for another episode of our free response question advent calendar. Thanks for watching.